Hello and thank you for joining us once again for another Pro Training Power Hour brought to you by Standard Motor Products. The topic today is external airflow, meaning the air that comes through the grille of the vehicle that keeps the condenser, the radiator, the power steering cooler, the engine oil cooler, the transmission oil cooler, charge air cooler, all the heat exchange components that are typically mounted behind the grille on a modern vehicle. I think I counted as many as 8 on a later model diesel application recently. Our focus will be particularly today as it relates to air conditioning performance, in other words, condenser airflow. But of course, the general principles apply to airflow through all these heat exchange components. My name is Peter McArdle. I will be your host for this session. And without further ado, let's get underway. So here's how the presentation is going to break down today. We want to talk about the importance of external airflow, really understanding how important that is and how it is often overlooked when we're trying to diagnose an air conditioning performance issue especially, and any kind of an overheating issue. Viscous fan touches, both conventional and electro-viscous, how they work, some diagnostic tips. We will touch on electric cooling fan operation, and we'll wrap it up with a short discussion on active grille shutters. So if you like what we share with you today, don't forget to come back next month, August 7th at 12:15 Eastern, when we will be doing another Standard Motor Products Pro Training Power Hour. Standardbrand.com, click on the training tab, and you'll see a link there for the Power Hour training sessions, both what's upcoming, and you can review all the past ones there as well. So the importance of airflow. Here is a demonstration we did here several years ago at the training center. And what we're about to do here is to slide a piece of cardboard down behind the condenser in front of the radiator. In other words, we're going to block all airflow through the condenser and basically the radiator as well. And let's see what kind of effect that has. So here's the actual scan data exported from the scan tool and graphed here in the red and the green traces are the actual scan data exported from the scan tool when we did this experiment. And of course, it's pretty obvious. The red line here is that's the air conditioning high side pressure. That's graphed from the high side pressure transducer. And you can see that when we introduced the cardboard, high side pressure was about 220 psi. And within about 15-20 seconds, we got from 220 psi to about 450 psi. Right at the top of the red trace there is where we pulled out the cardboard. And you can see that within 15-20 seconds, the high side pressure went back down again, pretty dramatically, pretty rapidly. The green trace, of course, is engine coolant temperature, again, directly from the scan tool. You can see that it's basically is flatline, unaffected, around 200 degrees. But I think if you go about halfway over the graph, you can see that the engine coolant temperature actually dropped by a few degrees, by maybe 2-3 degrees. And of course, the reason for this is once we block the airflow through the condenser, now the hot air from the condenser is no longer hitting the front of the radiator. So in actual fact, the engine ran cooler, even though we've got a big piece of cardboard in there right up hard up against the front of the radiator. And so generally speaking, because the fans are hard up against the back of the radiator, things have to be in really bad shape before it starts affecting radiator fan airflow. But a lot of things can affect, like shrouds and so on, a lot of things can affect condenser airflow. Of course, the cooling system typically has a lot of redundancy built in, so there's a lot of excess cooling, or significant amount of excess cooling capacity in the radiator, in the engine cooling system, whereas the air conditioning system is much more delicately balanced. And the powerful visual takeaway here is by just interrupting airflow across that condenser for a very brief period of time, you can see that air conditioning head pressure virtually doubled. And so the takeaway, the key point I want to get across here is that anything that will affect, this is obviously a pretty dramatic effect, but anything that affects condenser airflow through the condenser will have a significant impact on air conditioning performance. That's really the point I want to communicate here. So, when you look, this is the front end, I think, of a mid-2000s Power-stroke diesel Ford, and you can see typically in the front of modern vehicles now, there's 4, 5, 6, 7, I think I counted 8 recently on a particular application. There are many heat exchange components, power steering coolers, engine oil coolers, transmission coolers, the condenser, the radiator, and so on. So there's a lot going on here. It's absolutely vital that we have adequate airflow across all these heat exchange components for good vehicle longevity and the proper performance of all these different systems on the vehicle. So in our experience, inadequate airflow, it's a common undiagnosed because it can be, air is invisible typically, so it's hard to see. It's often an undiagnosed cause of premature compressor failure, poor air conditioning performance, engine, transmission overheating, and so on. Typically, if I suspect I have a radiator or a fan airflow problem, I'm going to look in 4 main areas: fan shrouds, bodywork integrity, missing air dams, etc. Was the vehicle in an accident, for example? We see this a lot, where the vehicle was in an accident, especially cars that have a lot of intricate pieces around the grille and around the headlights and so on. Little rubber strips and weather strips and air dams get left out. The vehicle may look fine, but the airflow through the grille and through the condenser radiator assembly can often be dramatically affected by parts that are left out after, following an accident repair. Debris, of course, oftentimes you look into the grille, the condenser looks perfectly fine, but it's often the area between the condenser and the back of the condenser and the front of the radiator. Oftentimes that's where tumbleweed and debris of all sorts accumulate. So it's very important, and it's not always easy to see. Sometimes you might even want to use a video borescope, something like that. You need to be sure to look down between the back of the condenser and the front of the radiator, be sure there are there's no debris in that area. Another important point I want to point out in connection with shrouds. If you look at the back of a lot of condensers, they will either have a little weather strip on either side, or maybe sometimes a little piece of foam, and it creates a seal between the back of the condenser and the front of the radiator. If those weather strips or seals are left out, it can have a dramatic impact on airflow through the condenser. The radiator will still get its share because the fan is right up against the back of it. It draws air in through the radiator. It'll come in from the sides if it has to, but if those weather strips are missing between the back of the condenser and the front of the radiator, it can have a dramatic impact on condenser airflow. The complete operating envelope, and what I mean by that is whether it's a viscous fan clutch or an electro-viscous fan clutch or it's an electric fan, we need to understand how the system operates. If I look at a cooling fan circuit, there could be quite a number of pressure and temperature inputs to the computer to get the fan to run at all the various speeds and permutations that are necessary. The same thing for the electro-viscous fan clutch. The computer is typically looking at 4, 5, 6 inputs to decide at exactly what speed that viscous fan clutch should run at. So we need to understand that. We'll touch a little bit on that. We need to understand that when we start to diagnose these things. So let's take a quick look here at how how electro-viscous and conventional viscous fan clutches actually work. So just a quick history here, of course, back in the 60s and 70s, typically the fan on most vehicles was it was a solid fan. The problem with these is it takes a significant amount of horsepower to drive them, especially at higher speeds. And at higher speed, when you're going down the highway, that's when you need the fan assist the least, and it's when it's wasting the most energy. So old school solid fans were pretty wasteful of energy. They were noisy, and of course they were dangerous because they were coupled directly to the engine, basically. When you went 4, 5, 6,000 RPM, well, the fan was doing 4, 5, 6,000 RPM as well. Then along came the non-thermal fan clutch up top in the middle there. This is a viscous coupling. There is no mechanical coupling between the water pump shaft, if you like, and the fan blades. It's a fluid coupling inside, and the non-thermal version of these clutches is constantly constantly engaged. In other words, the viscous fluid is in the working area all the time. If the engine is running, the fan is going to be turning. What is different is that because of the design and because it's a viscous or a soft coupling, if you like, as the engine speed gets above 2,500, 3,000 RPM or so, the discrepancy between fan speed and engine speed increases. So basically, it limits the top end fan speed to around 3,000 RPM or so. So we don't have that, it reduces the noise issue, and it's significantly safer than a conventional solid fan. Building on that technology, then, we have a conventional old-school thermal fan clutch. And I think you can see in the front there, it's got a thermal spring. That thermal spring, it's a bimetallic spring, and two metals are kind of bonded together, and it's wound. And so as the hot air coming off the back of the radiator hits that thermal spring, it unfurls, and it causes a gate to open or close inside to meter viscous fluid into the working area of the clutch, and I will explain how that works in a little moment. On the right, of course, is an electro-viscous fan clutch, and that fundamentally it works. It's the same type of viscous coupling as a thermal clutch, but here we've replaced the thermal spring with a computer-controlled solenoid, so we can more precisely control the engagement and disengagement of the fan. Now, just big picture here, there are a whole, depending on the size of the vehicle, the size of the engine, and how much real estate we need to cool. Some of the older Asian import vehicles with small 4-cylinder engines would have a 5 or 6 inch diameter small fan. And then we have the non-thermal that I discussed a moment ago, heavy duty, severe duty truck fan. As the bigger the vehicle we're working on, the bigger the fan clutch we need to keep the air moving, to keep it cool. And of course, the more recent technology now in the past 10, 15 years is electro-viscous fan clutches, where we put the computer in control of fan engagement. Now, this is just a fan clutch pulled apart here, so you can, a conventional thermal fan clutch, so you can get a sense of the pieces that are inside of it. Of course, the spring in the front, and then the front cover there. That plate, that inner cover that you see there, that's what separates the reservoir where the fluid is stored from the working area of the clutch. And again, we look at in more detail in a moment. The other thing I want to touch on here, if you note the bearing, there's typically only one bearing in these, although I think I've seen a few more modern designs where there may be a second bearing, but typically there's only one bearing in these fan clutches. And if you've ever held up a bicycle wheel and spun it in your hand while holding the axle, there's a significant amount of called precession, or the significant amount of stress on that bearing. You've probably often heard that when the bearing in the water pump goes bad, that you should replace the fan clutch. Well, believe it or not, there's very significant stress on that bearing as the vehicle turns back and forth. The centrifugal force of the fan creates significant stress on that bearing, and because of the very fine clearances inside the fan clutch, it doesn't take much wear in the bearing until you start getting interference between the landing grooves, between the coupled, the driven and the driving parts inside the fan clutch, and you get wear. You get microscopic aluminum particulates sloughing off, and the fan clutch can eventually seize. So just want to emphasize that bearing. We'll talk a little bit about that in a moment. In fact, while we're on this slide, a good practical check here, just to kind of for old school seat of the pants function check of a conventional fan clutch is, if it's a hot summer day, the air conditioning is on, and that fan should be engaged, and you're trying to figure out, is it engaged or not? One thing you can do is, run the engine at about 1,500 RPM, 2,000 RPM, watch the fan, and then shut the engine off. If the fan is truly engaged, if there's fluid in the working area of the clutch and the fan is actually engaged, typically the fan blades will slow down in about a turn and a half. If the blades continue to freewheel, and that the environment is such that the fan should be engaged, the blades freewheel, then the fan clutch is absolutely, it's an outright failure. It doesn't tell you that it's maybe partially failed, which is the harder one to diagnose, but it does tell you you've got pretty much a critical failure. The other check you can do is to grab the tips of the blades and rock them back and forth. You shouldn't, at the very tip of the blade, you shouldn't see more than about a 1/4 inch play at the very tip of the blades. That's checking on the bearing, of course. And also the little shaft, the shaft that thermal spring turns, comes through the front cover there. Check that there's no oil or fluid, or oftentimes if there's a kind of a dust telltale around the center of the shaft there behind the thermal spring, that's a giveaway that the clutch may be actually leaking. So we're going to look on the cart here how these things work. The red area in the front is where the reservoir, that's the reservoir, that's where the fluid is stored. That brighter green piece in the middle is the plate that separates the cover, that separates the fluid from the working area, and then the darker green area there is the landing grooves, the working area of the clutch. I've got a few taken apart here. We'll look at those in a moment. And then, of course, the very latest technology, like I mentioned, the thermal spring was the initial, thermal fan clutch. That was the initial design of these things. But in more recent years now, all manufacturers have replaced the conventional thermal clutch with an electro-viscous fan clutch. Now, the big advantage here is that the electro-viscous fan clutch has a speed sensor inside, so just like a camera or current sensor, the computer knows exactly how fast the fan is turning, and it's got a duty cycle control solenoid. Just think of an injector or each earth control solenoid. By varying the duty cycle to that solenoid, we can meter more or less fluid into the working area of the clutch to get the fan to speed up or slow down. So, just very quickly, there are several different designs of these. I will look. I have a couple on the cart here. We'll look at them as when we transfer to the carts in just a moment. The other important thing to understand here from a diagnostic perspective, when the electro-viscous fan clutches came out first, mid-2000s, GM was really the first to the party with this technology. And you can see here, looking at the clutch itself, very simple. I've got a solenoid, and I've got a hall sensor, speed sensor, think camera crank, that's going to report, it's typically got a 5-volt reference ground and a signal. It's going to report fan RPM back to the computer. What's the thing to note here is that on the early GMs, the solenoid was not controlled directly by the PCM. Note that there is a relay, and it plugs in. It looks like a conventional relay, but it's actually a solid-state relay. We'll plug into the fuse relay panel onto the hood. And the relay duty cycles the positive side of the solenoid. The computer provides a ground control to the input of the relay, but the relay itself actually pulses the power on and off to the solenoid. So it's the relay is a kind of the driver for the solenoid, and the solenoid itself is actually positive side control. So just keep that in mind. When we go to Ford or Ram, Dodge, it's kind of reversed. There is no more relay, so the computer is in fact in direct control of the solenoid, and you can see here that the solenoid is getting direct. Usually, sometimes it comes from the computer, but typically direct ignition voltage from an ignition source, and the computer, just like an injector or conventional solenoid, the computer duty cycles the ground side of the solenoid to control, the higher the duty cycle, the faster we want the fan to go, the more fluid we're going to meter into the working area of the clutch. Note also that it's got a spike selection diode there. So I want you to really think about this slide here, because the black line represents shaft speed. That's basically the water pump shaft speed, which of course is going to be directly related to engine speed. And the red line represents fan fully engaged speed, right? And the green line represents fan disengaged speed. And the thing that you have to understand here is we can perform that seat of the pants test I described previously to see if the fan is engaged at all. The real difficulty is determining, is the fan properly engaged given the temperature and the circumstances, the AC pressure and so on, all the environmental forces acting on the system. Is the fan turning at the right speed? And so especially with the conventional viscous fan clutches, thermal fan clutches, it can be very difficult to tell with the naked eye, is the clutch really engaged and turning at the right speed. I think there was a study done here several years ago, and some data suggested that up to 40% of fan clutches on the road were typically underperforming. They were working, but they were not engaged at the proper speed for the head pressure, temperature, and so on. The other thing I want to emphasize also while we're on this slide, remember the airflow slide we had earlier where the head pressure doubled while engine temperature remained the same. The other key takeaway from that is if you're depending on engine temperature, if you're looking at the temperature gauge in the dash as a guide to a possible airflow problem, you're almost certainly going to be misled. And what a point I'm making here is that oftentimes, it's a common sense approach. If you thought you had a condenser or a radiator airflow problem, you would think that if I have an airflow issue, well, wouldn't the engine, it might not be overheating necessarily, but surely it would be running hotter than it should. Well, as you can see from the earlier graph, in fact, there was we had a significant reduction in airflow, and yet there was absolutely no evidence of engine overheating. And so it is, like I say, it is using engine temperature as a guide or as an indicator of a possible airflow problem, especially a condenser airflow problem, can be very misleading and it's virtually worthless in fact. So, of course, a very common problem. This has been around now for several years. Most of you have probably heard of it, but it's quite common. We have a tech line here at our training center. We still get a lot of calls on this issue where, 03 and up Dodge Ram diesel trucks use an electro-viscous fan clutch, and the fan clutch fails. And of course, when the fan clutch fails, air conditioning head pressure goes to the roof. Air conditioning does not work well, especially at slow speed and stops. And eventually the compressor fails. And oftentimes we find the shop replaces the compressor, doesn't identify the fact that the fan clutch has failed, and so the compressor gets replaced, and it fails repeatedly because the viscous fan clutch has not been diagnosed and replaced. Often going along with that is this vehicle uses a liquid line, a captured orifice tube in the liquid line, and the liquid line does not get replaced. In other words, the orifice tube does not get replaced. Debris gets stuffed down the liquid line, the compressor fails repeatedly, and we get into, as you can imagine, we get into trouble there. The other big input, obviously the computer is looking at temperature, engine temperature, coolant temperature, and so on, to control the application of the electro-viscous fan on these trucks. But the AC high side pressure transducer is also a fairly common failure on these, and also on Fords. Fairly common failure. They can leak, both with the screw onto the line, right in the middle there where there's a roll seal, between the terminals where they come out through the plastic. And the other big thing I see on them is they go out of calibration. They go out of, they get shifted one way or the other. Sometimes if you're looking at scan data, you'll see the pressure kind of jumping around erratically, dead giveaway for the transducer being out of whack. And the other significant issue here is typically, again, no evidence of engine overheating on the gauge. And also, even if the computer may or may not set a diagnostic trouble code for the fan clutch, for the speed sensor, the solenoid circuit, depending on what's gone wrong with it, but because it's a Class C code, it does not turn on the check engine light. So, of course, nobody ever thinks to as you can see here, nobody ever thinks to check for trouble codes because the check engine is not on, there's no evidence of overheating, so basically we don't suspect the fan clutch. So don't forget, I've got a few of these samples here on the cart, we'll look at it in a moment. If you are, we get a lot of these returned looking like this, and obviously the folks did not have the proper tool for removing and replacing the fan clutches. It's very, they can be difficult to get off. You really need the right equipment, the right tooling to hold the clutch and to break the nut, to break the big nut loose when you go to replace one of these fan clutches. So that you can have an outright failure, of course, and then you can have a failure of degree, the difference between the red line and the green line that we discussed earlier. And so obviously if you have an outright failure, if you have a trouble code and so on, they're usually easier to diagnose on an electro-viscous computer control because you can look at fan speed and so on. And by the way, we will look, I have a vehicle set up here, I've got an F250 set up. We are going to look at some live scan data before we wrap up today. But the picture on the right here, this is looking down from under the hood on the top of, on the header panel, on the fan shroud, on a 2012, 2015, I think it is, F250 with a 6.7 liter diesel. And the point I'm trying to drive home here is that oftentimes you're in there because the water pump has failed, or the compressor has failed, or the alternator has failed, or the idler pulley has failed. Look, I'm not saying that you should replace the fan clutch every time you go in there, but certainly if I have to start taking that shrouding apart, there's significant labor involved. I'm certainly going to look hard at the fan clutch data, looking at the fan bearing. I'm going to be at least evaluating the fan clutch before I go in, if I have to go in there to replace any other components. So before we do that, let me go to the cart here. We'll spend a few minutes just explaining how some of these fan clutches work. So of course, here is this is the conventional thermal clutch. These are in, it is a viscous coupling. You can see I can hold the part that we've connected the fan blades here, and I can turn it. And this is there is no working area versus reservoir. This fan clutch is basically engaged all the time, but as the engine RPM increases, the slippage becomes greater and greater. So it saves some energy, reduces noise, and limits the top end fan speed to around 3,000 RPM or so. So then, of course, now I've got my this is a conventional thermal viscous fan clutch. There's my thermal spring in the front. And now the first iteration of electro-viscous was GM in the mid-2000s. I think the Trailblazer, 05 Trailblazer would be the first application if I'm not mistaken. And again, inside, and we will look inside in one moment, inside it's a conventional viscous drive. The difference is that instead of a thermal spring that operates very slowly, unfurls and contracts rather slowly, so it's very slow to respond. By putting the solenoid inside and duty cycling that solenoid, I can control the flow of the fluid much more quickly, so I can get the fan speed to respond to changing conditions much more rapidly. And of course, inside here is a speed sensor, a Hall effect speed sensor, just like a cam or a crank sensor. So let's look inside a fan. So here's a cutaway of a typical fan clutch. You can see I've got my thermal spring here in the front, and inside here, right here, I'll just hold it up a little bit to the camera so I think you can see. Right here is the working area of the clutch. And you see it's like a tongue and groove. They're interwoven like this here. And if I pump viscous fluid into this area here, I can create that stiff, I can create that viscous. It's never solid, it's never a hard mechanical connection, but I can create a very, a significant viscous coupling between the water pump shaft and the cooling fans. Now, in the front here, there is a reservoir area, and then when the thermal spring expands, it rotates a shaft right there in the center. It rotates a gate inside. So you can see there's a hole right there. Now you may be able to see this. It's kind of hard to see, but I will try to. So you can see the gate. You can see the gate coming into the area there. And that's when that gate opens, the fluid is forced from the reservoir through that gate into the working area of the clutch. Centrifugal force forces it out to the outer circumference of the clutch, and there's actually a channel. There's a channel drilled in the aluminum, and the fluid, when the clutch is working, the fluid is actually continuously it's being pumped from the reservoir through the open gate into the working area of the clutch, out to the outer surface, and back through a drilled channel in the cover here, back into the reservoir. So it creates a kind of a circulation effect. And that's necessary also to make it work. So we can increase the speed, decrease the speed, and also the circulating fluid keeps the clutch, the working area, cool. The shear stress creates a lot of heat buildup, and so you need to circulate the cooling. That's why there are cooling fins in the front area of the clutch here. So that's a conventional viscous fan clutch. Now, let's look at what an electro-viscous fan clutch looks like. So you can see here. Here is the solenoid assembly. This is the solenoid assembly. So inside of here it's just a simple Hall effect type speed sensor. and a solenoid, a duty cycle control solenoid. And if we look in the front, here's the clutch. This area here, in this area here, is the fluid, is the viscous fluid. And this is the cover that separates the reservoir from the working area of the clutch. By the way, just for the record here, this is the silicone. This is actually a bottle of the silicone fluid here. There's about 7 or 8 different viscosities of these fluids. It's all a very kind of precise science, temperature and shear stress and fan diameter. There's a lot of science goes into the design and development of these fan clutches. So this is the viscous fluid that would go in the working area here that creates the viscous coupling. So recall that on our conventional fan clutch, we had a plate, a little gate that rotated in the back like this. This is the GM design. This is what we call a linear. This is the linear design. This is the GM design that you can see here. So that, of course, the solenoid with the speed sensor screws in the front housing, in the front cover of the clutch. And when we duty cycle the solenoid inside here, we create a magnetic field. The higher the duty cycle, the stronger the magnetic field. And that pulls back on the gate here. And you see it's actually opening up by just pulling it back by a tiny amount, increasing the strength of the magnetic field, by increasing or decreasing the duty cycle command to the solenoid, we can meter more or less fluid out of the reservoir into the working area of the clutch. So here's the actual, here's the tongue and groove. So we put the two together, and there you've got a viscous. If I fill this area inside here with fluid, I can pump the fluid from the reservoir area here in the back into the working area of the clutch. And actually there's the port right here. That's the port. So the fluid gets pumped in here, and then the centrifugal force forces it out to the outer edge, and it's pumped back into the reservoir here. So you get a kind of a circulating effect within the fan clutch. So that's the linear fan clutch design. Now, here is so now you've probably seen this. This is your typical Dodge or Ford. I'll take a completed one out here. This is your typical Dodge or Ford electro-viscous fan clutch, or as Ford calls it, a Vistronic fan clutch. And this is what we call a rotary design. Now, it's the same basic concept. You've got a speed sensor, you've got a duty cycle control solenoid in there, but instead of pulling the little flapper back like you saw on the GM design, it's actually got a rotary, it's got a blade here. So so here's a conventional viscous fan clutch. Again, there's the gate. So when that thermal spring moves, it's controlling that gate, and that is controlling the amount of fluid that's metered through these holes here. So the Ford linear fan design, linear viscous fan clutch design, is a similar kind of a concept to the original thermal clutch. If we watch it here, I should be able to make it rotate a little bit. See how it's spring-loaded? So as that little flapper there controls the gate. So if I increase the duty cycle, I pull it farther, I uncover more of the opening in the cover. And so again, we can meter more or less fluid into the working area of the clutch. I should emphasize also, here is a kind of a cutaway, a kind of a pizza-shaped slice of the fan clutch here, and here you can get a little bit of a sense of the clearance between the driven and the driving plates and members inside the fan clutch assembly. By the way, the clearance here in an actual working fan clutch, the clearance between the tongues and grooves is just a few 10,000ths of an inch. That's why the bearing is so critical. The stress on that bearing with the centrifugal force of the fans is very significant, and that's one of the things. That's one of the reasons that you want to check for possible fan bearing failure. Here is a cutaway. There's an actual cutaway of an electro-viscous fan clutch, and you can see if we look inside the clutch here, Well, anyway, the little blades, it's 6, by the way. For every revolution here, there's like 6 little reluctors. I was trying to get the reluctor out here, and it's refusing to cooperate. There's a little reluctor in here. It's got 6 segments on it. That's what creates there's a cutaway. You can see the solenoid winding here. The little vanes that create the speed signal are right out in the front here. So this is the cutaway there's the dividing plate, but there's the reservoir here, and of course this is the working area here and here of the viscous fan clutch. So this is the linear design over here. Now, you recall I talked about the bearing. So here is a classic example of see if I'm holding it tightly here, but this fan clutch is seized. This was making a terrible racket, very noisy. The fan was getting up to full engine speed. And again, this is because while it feels all tight and firm here now, the original cause of the failure on this fan clutch was the bearing got too sloppy. Then you get interference inside between the land and grooves, and aluminum starts building up in the working fluid, and eventually the whole assembly seizes. So this is a classic example of a failed viscous fan clutch. So, and here I was referencing earlier, here is the Dodge, the 03 and up Dodges that use the electro-viscous fan clutch. Where the fan clutch goes bad, causing repeat compressor failure. Here, I think if you look very carefully right here and right here, these are the crimp marks. This is the orifice tube is actually crimped inside the liquid line here, and that often gets overlooked. The orifice tube doesn't get replaced, and the debris from several failed compressors literally gets stuffed down the line, and around we go. So, I did reference, or I mentioned previously also, there are a variety of tools. I'm not. I will point out that the conventional viscous fan clutch, they're assembled in a temperature-controlled room at 72 degrees, so that to set the base calibration of the fan. So I prefer using manual tools when I'm working on a viscous fan clutch or replacing it, taking it on, putting it off. This is acceptable. This is an impact wrench with a special adapter kit for taking off viscous fan clutches, but I personally prefer working with manual wrenches and tools for replacing, like this one, like this example here. Okay, that's my preference for removing a viscous fan clutch. All right, so we have a truck set up here today. It's a 2012, I think, 2012 or 2015 Ford F-250. I am going to climb aboard. So, I've turned the ignition, I had it running earlier. I hope I have gathered the appropriate data together that we need to look at here. And now I've gone, we're a little bit short for time. So normally I would go into regular data, review the data. If I was investigating an overheating problem, an air conditioning performance problem, I would look at oil temperature, transmission oil temperature, AC head pressure, and so on. There's a variety of data that you might look at trying to get a handle on, trying to get a clue as to what's causing your problem. But I've gathered where there is a bidirectional function for testing these fan clutches on most scan tools, and I've gone straight into that test. So I have variable fan duty cycle with the scan tool. We should be able to increase and decrease the duty cycle command to the solenoid so that we can try to determine if the fan clutch is working. So we're key on, engine off here. You can see AC head pressure. It's a live reading. High pressure is about 117 psi. I think it's about 80 psi in the shop, 80 degrees in the shop right now. Head pressure 117. That's to be expected. The truck was running previously. Actually, right there, ambient air is 78, almost 79 degrees. Engine coolant temperature is not quite warmed up, about 140, 150 degrees. We haven't. So let me go ahead and start it up here, and let's see what becomes apparent pretty quickly. So I've used the scan tool. I've reduced the command duty cycle command to the solenoid to 0 for now. And the things I want you to note here. So note already, right off the bat, that air conditioning head pressure is 200, over 200 psi. So when an 80-degree day, 75 and 75 be 150, and maybe half of that again. So somewhere between 150 and 200 psi, 2 to 2.5 times ambient temperature should give me high side pressure, roughly. And so I'm around 100. Now note here that the fan is, the Vistronic cooling fan is at about 800 RPM. So I'm going to increase the engine RPM slightly here, and that's the problem with viscous fans. When the engine is off, the fluid leaks can weep into the working area, especially on electro-viscous fan clutches. On conventional thermal fan clutches, we incorporate an anti-drain back valve, so that if the clutch was off when you parked the vehicle, it should be off when you start it up the next morning. But in this case here, I'm going to increase the engine RPM a little bit, and we're going to watch what happens to see. We've got the fan clutch duty cycle at 0, and we're going to watch what happens to the cooling fan speed. And what should happen, if I give it a little minute here, it should eventually pump because we're not sending a command to the solenoid, it should pump the fluid out, and eventually that fan speed should start falling. So that brings me to the first point I want to make here. It is a viscous coupling, so it takes time. Can take up to 90 seconds. It can take time to pump the fluid out of the reservoir into the working area of the clutch to get the RPM to ramp up to the desired speed. And then, of course, if I want to reduce the fan speed, it takes time to pump the fluid out of the working area and back into the reservoir. So while electro-viscous fan clutches are much more responsive than conventional thermal fan clutches, they are still, it's still a relatively slow process before the, for the fan speed to change. So you can see here now that this fan, it's still, the engine RPM is 800, the fan is still turning quite fast. So if I give it a minute here, it should, the fan speed should eventually, and so you see, we're not sending a command to the solenoid, yet the cooling fan is still turning quite fast relative to engine speed. And the engine temperature is only 149 degrees, and the fan desired duty cycle percent is 0, because the engine temperature is low, engine AC head pressure is only 150, 160 psi. There's no need for the fan to be turning particularly fast right now, and that's why the command is virtually 0. But as you can see, it's actually taking some time here for the cooling fan speed to change. I think I just heard it, I believe. So now you see how the fan speed is dropping very dramatically now. So now the fan speed has dropped to 400 RPM. The engine is actually running about 600 RPM. Fan speed has dropped to 275. Now you see it took the best part of a minute or two to pump the fluid out of the working area of the clutch back to the reservoir. And in fact, if I start increasing, if I go to increase the duty cycle command to the fan speed, you will note that it's actually it'll take a significant amount of time for the fan speed to increase. And in fact, look at my air conditioning high side pressure is 230 psi right now, which is 30-40 psi higher than I would expect it to be. And that's because the fan speed has dropped way down. And so what I'm emphasizing to you here is that there is always, when you look at commanded speed versus actual speed on an electro-viscous fan clutch, regardless of what application you're looking at, there will be a lag time between the command. It takes time to get it up to speed and to slow it back down again, and that's what we're looking at here. The other thing I want to point out here that can be confusing, do you see that the fan speed desired RPM is 1100 RPM and the engine is only running at 600 RPM? Well, if you do the math, if you look at the two pulleys, they're almost the same size. Right now, it would be, even if the fan was mechanically coupled to to the crankshaft, it probably wouldn't turn at 1100 RPM. So the desired speed here is probably unattainable because the engine is turning so slowly. So you really have to look at the data and understand what's going on to understand what's going on with the fan speed. But right here, where you see the duty cycle command is 98%, and yet my fan speed is still only 400 RPM. My high side pressure is still high. So we've done some work with this truck. My sense already with this truck is that the viscous fan on this truck, the electro-viscous fan on this truck is lazy, it's probably sticking or binding, and it's taking longer than I would expect for the fan clutch to respond to both to speed up and to slow down, because it's taking too long to pump the viscous fluid into or out of the working area of the clutch. So again, just want to share some thoughts with you on how to approach using your scan tool to diagnose one of these electro-viscous fan clutches. So let me shut it off there right now, and we will continue with our presentation. So when we broke off before, we were going to talk about electric cooling fan service very quickly. Again, we've talked quite a bit about viscous fans so far, but electric fans on paper are pretty simple, a 2-wire motor typically. But the thing to understand about electric fans is the circuits and the strategies used to control them can be quite complex. Do you have one fan or two fans? Do both fans run in parallel, meaning do they both come on at low speed together, then go on to high speed together? Do you have a dedicated radiator fan versus a condenser fan? How you can have pressure inputs, several pressure inputs, the temperature inputs, and so on. The strategies and the components and the switches and the pressure transducers controlling fan speed can be quite complex. So you kind of really have to sit down with your information system and look at the wiring schematic, look at pressure and temperature threshold of various sensors and switches to really understand. Because oftentimes, the reason I'm emphasizing this, oftentimes you will have a vehicle that's not overheating, but just like we discussed before with the viscous fan clutches, the vehicle is not overheating, yet the air conditioning is not working as well as it should. The head pressure is way through the roof. And oftentimes that's because either one fan is not coming on when it should, or a pressure input that we need to bring that fan on is is skewed or out of calibration, or maybe not there at all. So again, electric fan circuits and strategies can be quite complex. So the PCM is probably looking at engine temperature, transmission oil temperature, charge air cooler. Could be looking at a variety of inputs to decide what speed to run the fans at. Many modern systems now, of course, use duty cycle control, where the fan speed is not just 1 or 2 or 3 speeds. The fan speed can be controlled incrementally with with a duty cycle controlled relay or control module of some kind. It's certainly most modern systems, when the air conditioning head pressure goes above a certain threshold, it's going to trigger the fan. And even road speed, at highway speed, the expectation is that you're going to have enough airflow through the radiator condenser assembly that you're really not going to need fans in most circumstances. So we're not going to go deep in the weeds here, but this is from an older 2002 Toyota Camry, and you can see, I think I counted 4 between temperature and pressure inputs. There are 4 different switches for pressure thresholds, temperature thresholds. There are 3 different relays. Typically, these fans can be run either at slow speed, where the 2 fans are run in series with each other. They're wired, the relays configure in such a way that the fans are wired in series with each other, so they run at half speed. And then the relays are reconfigured to make the fans run at full speed, giving them both full system voltage. And in addition to all this pressure and temperature switches, you can see here that the computer, looking at engine temperature, can also turn on the fan. So you can imagine if you have a cooling system issue, an overheating issue, an air conditioning performance issue, you might have to sit down with the wiring schematic to understand exactly how these fans work and confirm, satisfy yourself that all the pressure and temperature thresholds are being met for all these different switches. So just looking at that one circuit alone, there's, I think, 2 temperature switches, a pressure switch, and there's 3 different relays that are necessary to get those fans to run at all the appropriate speeds. And so, just reiterating the importance of electric fans, I think you understood from my graph earlier how important airflow is. Here's a classic example here where we had about a 1.7 volt drop on the cooling fans. It was a Dodge Charger, as I remember. We had a 1.7 volt drop onto the cooling fan motor, and the air conditioning, it worked, but it just wasn't quite as cold as we would have expected. And you can see over here on the left-hand side, after we replaced the relays, the fan speed was about 20 to 2200 RPM, and then before the repair, the fan speed was about 1800 RPM. So you can see that replacing the relay here increased the fan speed about 268 RPM. That's about a 12% drop from after the repair versus before the repair, about almost a 300 RPM difference. And in the next slide here, looking at our scan data, you can see there's about a 20. When we replaced the relay, the AC head pressure dropped about 25 psi. So again, airflow, very important and critical for air conditioning performance. Cannot overemphasize that enough. So this was a little Chevy Sonic, just a kind of an abbreviated, a shortened case study here. The air conditioning did not work well at stops when the car came to a stop, and the engine temperature, the temperature gauge, would start creeping up. So a quick inspection showed that the cooling fans were not working, were not coming on. The technician found the 40 amp fuse blown in the relay box and decided to put a jumper across it with his scope, using an oscilloscope with the current probe. And when he turned the fans on, when he ran the vehicle and the fans come on, you can see that the current ramped up to almost 130 amps here. And even when the spike went away, the current is still running at about, I think it's 45, 50 amps here. And so obviously the fans were, probably the brushes worn, the bearings binding, the fans were on the way out, and it was, popping the relay. With the fan replaced, you can see the initial current spike is dramatically less. It only gets to about 50 amps on that initial spike and then settles down to around 25, 30 amps. So a much, again, this is why it's very important to check. I mean, as a routine, if I'm doing significant air conditioning repairs or service on the vehicle, I will often check the cooling fan current draw and the voltage available at the fans. So the takeaway is to routinely check cooling fan voltage and current draw and replace relays if necessary. So to wrap up our session today, we're going to talk about active grille shutters. Now, I'm not going to get in great detail here because if you go back and look, if you go to standardbrandtraining.com or standardbrand.com and click on the training menu, training option, you would see just last year we did a whole session on active grille shutters, so you can go back and review that session. We get into a lot more detail than we're going to get into today. I emphasize them though because they're critical for airflow. I've seen many repeat compressor failures because active grille shutters, somebody ran over something on the highway, the grille shutter is stuck closed. Usually doesn't cause a significant engine overheating issue, but it will cause it'll have a dramatic impact on air conditioning performance. The whole idea behind these things is to reduce the airflow through the front grille and so on, so you get much smoother, the air goes around the vehicle rather than through it, so that reduces the coefficient of drag on the vehicle, so you get better fuel economy, reduced emissions, and reduced wind noise also at highway speed. Another significant thing is Toyota did a study, I think I read something recently, where in cold weather in the wintertime, cabin warm-up time is literally twice as fast because they keep the active grille shutters closed during engine warm-up, so you get much faster cabin warm-up with the grille shutters closed. So obviously if the grille shutters were stuck open, the customer's complaining about poor heating performance. That could be the very reason. So they're usually closed at highway speed and during engine warm-up to accelerate cabin warm-up and reduce the warm-up emissions. And they're open as necessary. I mean, I know Nissan has a strategy over 88 miles per hour. I think the fans open at highway speed to prevent wind damage to the shutters and so on. Air conditioning head pressure is a big input. Obviously, transmission engine temperatures are a big input. And there's also there's ice protection strategies so that they don't freeze in the winter. There's a lot goes on behind the curtain when it comes to the operation of active grille shutters. So, again, go back and look at that previous power hour. If they're stuck closed, which is usually the bigger concern, you're probably going to have engine overheating and air conditioning performance issues. If they're stuck open, again, fuel economy will be affected, especially in colder temperatures where it takes longer for the engine to warm up, and the customer will almost certainly complain that the cabin doesn't warm up nearly as quickly as it used to. Now, again, the big dollar issue here is I have seen compressors replaced repeatedly, because the head pressure was getting too high, putting excessive stress on the compressor because the grille shutters were stuck closed. Again, standardbrand.com, you can look at what's coming. Don't forget to join us on August 7th, 12:15 Eastern for our next Power Hour presentation. The topic is throttle body relearn procedures. And of course, you can, from this page also, you can review previous recorded webinars. So here's what we covered today: the importance of external airflow. Remember that graph showing the high side pressure versus engine temperature, how these fan touches work, some quick diagnostic tips, a little touch on electric cooling fan operation and diagnostic tips, and we finally wrapped up our conversation with active grille shutters. So with that, I will say thank you very much for joining us today. I hope you got something to take away from our presentation this evening, or this afternoon, or today. And thank you again, and see you again next month. Thank you.